We live inside a hole in the universe, not a black hole, something bigger, a cosmic void, a region of space where galaxies are rare and matter is thin. The Milky Way sits near the edge of a structure called the KBC Void. It's 2 billion light-years across, one of the largest empty regions ever discovered. And scientists only figured this out in 2013. For decades, we thought we lived in a typical part of the cosmos. Turns out, we don't. We're in a cosmic desert, and this changes everything we think we know about dark energy, the expansion of the universe, and why our measurements keep contradicting each other. If you're ready to learn why living in a void might solve one of the biggest mysteries in physics, hit that subscribe button. The revelation starts now. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie published a paper that made cosmologists uncomfortable. They analyzed the distribution of galaxies around the Milky Way, mapped thousands of them, measured their distances, plotted their positions in three-dimensional space, and they found something strange: a massive underdensity, a region where galaxies are far more spread out than they should be. They called it the KBC Void, named after the three scientists who discovered it: Keenan, Barger, Cowie. The void is roughly 2 billion light-years in diameter. Our galaxy sits about 1 billion light-years from the center, not at the very edge, but close enough to the boundary that we're technically inside it. And when you're inside a void, you see the universe differently than someone living in a dense cluster of galaxies would. Here's how voids work. The universe isn't uniform. Matter clumps together under gravity, forming galaxies, then clusters of galaxies, then superclusters. These dense regions are connected by filaments, long chains of galaxies stretching across hundreds of millions of light-years. Between the filaments are voids, vast empty spaces where galaxies are rare. Most of the volume of the universe is actually void, empty space with almost nothing in it. Voids aren't completely empty. They contain some galaxies, just far fewer than average. In a typical region of space, you might find hundreds of galaxies within a sphere 300 million light-years across. In a void, you might find a dozen. The density can be 10 times lower than the cosmic average, and the KBC void is one of the largest ever discovered. Only a handful of voids this big are known to exist, and we happen to live inside one of them. At first, this seemed like a curiosity, an interesting fact, but not particularly important. But then cosmologists realized something. If we live in a void, and voids have lower density than average, then our local measurements of the universe's expansion rate might be wrong. Not wrong because of bad instruments or bad math, wrong because we're measuring from an atypical location. And that might explain the Hubble tension. The Hubble tension is one of the biggest unsolved problems in cosmology. Two different methods of measuring the universe's expansion rate give two different answers. Measurements based on the early universe, using light from when the cosmos was 380,000 years old, predict the expansion rate should be 67 kilometers per second per megaparsec. Measurements based on nearby galaxies and supernovae give 73. That 6-unit gap shouldn't exist. Both measurements are precise, both have been checked and rechecked, yet they disagree. Living in a void might explain why. Inside a void, space expands slightly faster than average, not because dark energy is stronger here, but because there's less matter pulling things together, less gravitational drag. If we're measuring the expansion rate from inside a void, we'd get a higher number than someone measuring from a dense region would. And that higher number would be correct for our local environment, but not representative of the universe as a whole. It's like measuring the temperature inside an air-conditioned building and concluding the planet is colder than it actually is. The measurement is accurate for your location, but your location isn't typical. Act 2. How big is the void? 330 to 615. Let's talk scale, because 2 billion light-years is a number so large it loses meaning. Here's a comparison. The Milky Way is 100,000 light-years across. The nearest large galaxy, Andromeda, is 2.5 million light-years away. The local group, the collection of about 80 galaxies we're gravitationally bound to, spans about 10 million light-years. The supercluster, a much larger structure containing thousands of galaxies, is about 110 million light-years across. The KBC void is 2 billion, 20 times wider than the Virgo supercluster. It contains our local group, the Virgo supercluster, and thousands of other galaxies, all of them spread thin across an enormous volume. If you could see the cosmic web from outside, it would look like a sponge. Dense filaments of galaxies forming walls and sheets, voids in between. The KBC Void would be one of the largest bubbles in that sponge, and we'd be a tiny speck inside it, closer to the wall than the center, but still deep enough that the void's properties affect our observations. Here's what makes this discovery controversial. The standard model of cosmology, the lambda CDM model, predicts how large voids can be. There's a maximum size based on how matter was distributed in the early universe and how gravity has pulled it together over 13.8 billion years. According to the model, voids larger than about 1 billion light-years should be extremely rare. The KBC Void is twice that size. Some astronomers argue it's too large to exist, that if it's real, the standard model needs revision. Others say it's within the range of possibility, just barely, and we happen to live in one of the universe's largest underdense regions by chance. But there's evidence the void is real. Multiple independent studies have confirmed it. Surveys mapping galaxy positions show the same pattern. A large underdensity centered roughly where the Keenan-Barger-Cowie team said it was. The void isn't just empty of galaxies. It's also empty of galaxy clusters, those massive gravitationally bound collections of hundreds or thousands of galaxies. In a typical region, you'd find several clusters within a billion light-years. In the KBC Void, there are almost none. That's not a measurement error. That's a real deficit of structure. And the void explains some other oddities. For years, astronomers noticed that our local group of galaxies is moving in a particular direction. Not just expanding with the universe, actually moving through space, pulled by gravity, towards something. That something is called the Great Attractor, a massive concentration of galaxies about 150 million light-years away. But even the Great Attractor doesn't fully explain our motion. There's another pull, from even farther away, called the Shapley supercluster. We're being drawn towards the edges of the void, towards regions of higher density. Which makes sense. Voids repel, dense regions attract. If you're inside a void, gravity pulls you towards the walls. This creates a problem for cosmology. The universe is supposed to be homogeneous and isotropic at large scales, the cosmological principle. It says that if you zoom out far enough, the universe looks the same everywhere. No special locations, no preferred directions. But if we live in a 2 billion light-year void, and that void is large enough to affect our measurements, then our location is special. We're not in a typical part of the universe, and that means our measurements might not be typical either. Some cosmologists are trying to use the void to explain the Hubble tension. They build models where the expansion rate varies depending on local density. Inside a void, the expansion is faster. In dense regions, it's slower. Average the two and you get the prediction from the early universe. Measure from inside a void and you get the higher local value. Problem solved. Except most cosmologists aren't convinced. The models work mathematically, but they require fine-tuning. The void has to be exactly the right size, with exactly the right density contrast, and we have to be positioned in exactly the right spot for the numbers to match. It's possible, but it feels like a coincidence, and physicists don't like coincidences. Here's where it gets really interesting. If we live in a void, and the void explains the Hubble tension, then maybe dark energy isn't what we think it is. Dark energy is the name we give to whatever is causing the universe's expansion to accelerate. About 5 billion years ago, the expansion started speeding up. Not slowing down like you'd expect from gravity pulling things together, speeding up, as if something is pushing space apart. We don't know what that something is, we just call it dark energy, and say it makes up 68% of the universe. The standard assumption is that dark energy is constant, the same strength everywhere, the same strength throughout time, a property of space itself. Vacuum energy, the cosmological constant, Einstein's lambda. Whatever you call it, the idea is that every cubic meter of space contributes a tiny amount of repulsive energy. Add up all the cubic meters in the universe, and you get enough push to accelerate expansion. This model works, it fits most of the data, but it has problems. One problem is the Hubble tension. If dark energy is constant, the expansion rate should be the same when measured locally as when predicted from the early universe. But it's not. Living in a void might resolve this. Inside a void, there's more space and less matter, more vacuum energy, less gravitational pull. The balance tips.
Expansion accelerates faster, not because dark energy itself is stronger, but because there's more of it per unit of matter. It's a relative effect, and it could explain why local measurements give a higher value. Another problem is the coincidence problem. Why is dark energy dominating now? For most of the universe's history, matter dominated. Gravity pulled things together. Galaxies formed, clusters formed. Expansion slowed. Then, 5 billion years ago, dark energy took over. Expansion started accelerating. Why then? Why not 10 billion years ago? Why not 1 billion years from now? The fact that we live in the exact era when matter and dark energy are roughly balanced feels suspicious, like we're living in a special time. And physics doesn't like special times any more than it likes special locations.
But if dark energy isn't constant, the coincidence problem goes away. If dark energy is dynamic, changing over time or varying with density, then there's no mystery about why it dominates now. It's just the current phase of a process that's been going on since the Big Bang. Some models propose that dark energy is a field, like the Higgs field, that evolves as the universe expands. Early on, the field was weak, matter dominated. As the universe grew and matter spread out, the field strengthened. Now it dominates. In the future, it might weaken again. If we live in a void and the void affects how we perceive dark energy, then we need to rethink our measurements. Everything we know about dark energy comes from observations. Supernovae, galaxy distributions, cosmic microwave background fluctuations. All of those observations are filtered through our local environment. If our local environment is atypical, our conclusions might be skewed. It's like trying to understand global climate by only studying weather patterns in one city. You'll get some things right, but you'll miss the big picture. The good news is we can test this. The European Space Agency's Euclid mission, launched in 2023, is mapping the distribution of galaxies across billions of light years. It's measuring the shapes of galaxies, how they're distorted by gravity, how they cluster together. The data will reveal the true structure of the cosmic web, including the boundaries of the KBC Void. If the void is real and as large as claimed, Euclid will confirm it. And if the void explains the Hubble tension, Euclid's data will show how the expansion rate varies with density. Within a few years, we'll know if living in a void is the answer or just a convenient excuse. Let's address the elephant in the room. If we live inside a 2 billion light-year void, are we special? Does our location in the universe matter? For most of modern cosmology, the answer has been no. The Copernican principle, the idea that we're not at the center of anything. Earth isn't the center of the solar system. The solar system isn't the center of the galaxy. The galaxy isn't the center of the universe. We're just one planet orbiting one star in one galaxy in a universe with trillions of galaxies. Nothing special about us. But living in a void challenges that. Voids are rare. Most galaxies live in filaments or clusters, dense regions where galaxies are packed together. If you picked a random galaxy in the universe, odds are it would be in a dense region, not a void. The fact that we're in a void makes us unusual. Not unique, there are other voids, other galaxies inside them, but unusual. And if our location affects our measurements, then maybe we've been wrong about some fundamental properties of the universe because we've been measuring from an atypical vantage point. Some physicists push back on this. They argue that even if we're in a void, the void isn't large enough to matter. The universe is 93 billion light-years across, the observable part anyway. A 2 billion light-year void is a tiny fraction of that. Measuring the expansion rate from inside it is like measuring the Earth's curvature from a hilltop. You'll get a slightly different number than if you measured from a valley. But average enough measurements from enough locations and the errors cancel out. The void might introduce a small bias, but not enough to explain the Hubble tension. Others argue the opposite, that the void is exactly the right size to matter, that we're living in one of the universe's largest underdense regions, and that region is just barely large enough to skew our local measurements. The probability of this happening by chance is low, but not impossibly low. The universe is big. Strange things happen. Maybe we're one of those strange things. There's also a philosophical angle. If we live in a void, and the void makes our environment different from the cosmic average, does that violate the Copernican principle, or does it refine it? The principle says we're not at the center of the universe.
But it doesn't say our local environment is typical. Maybe the universe is more varied than we thought. Maybe some regions are denser, some are emptier, and the properties we measure depend on where we are. That doesn't make us special in a meaningful sense. It just makes us local, subject to the conditions of our neighborhood. And here's the thing. Even if we're in a void, it doesn't change the big picture. The universe is still expanding. It still started with a big bang. It's still filled with dark matter and dark energy. Galaxies still form. Stars still die. Life still exists. Living in a void doesn't make the cosmos fundamentally different. It just means we need to account for our location when interpreting our data. Like adjusting for altitude when measuring air pressure. The measurement is still real. You just need context. The next decade will tell us more. Surveys like Euclid and the Vera-Rubin Observatory will map the universe in unprecedented detail. They'll measure the expansion rate from thousands of locations, not just our local neighborhood. They'll track how density varies across cosmic scales. If the KBC Void is real and large, the data will show it. And if it explains the Hubble tension, the correlation will be clear. And if it doesn't, if the tension remains even after accounting for the void, then we're back to square one, searching for new physics, new explanations, new ways to reconcile the contradictions. But right now, the possibility is real. We might be inside a cosmic hole, a 2 billion light-year bubble of emptiness. Not because the universe chose to put us here, but because voids exist, and we happen to live in one. And if that's true, then everything we thought we knew about the universe's expansion, dark energy, and our place in the cosmos needs to be revisited. Not thrown out, but adjusted, refined, made more accurate. We're inside a cosmic hole, the KBC Void, 2 billion light-years across, one of the largest underdense regions in the universe. And nobody told us because nobody knew until 2013. Living in a void might explain the Hubble tension, why local measurements of the expansion rate don't match predictions from the early universe. It might change how we understand dark energy, and it might mean we're in a slightly unusual part of the cosmos. Not special, just not average. The data is still coming in. Surveys are mapping the cosmic web in more detail than ever before. Within a few years, we'll know if the void is real, how it affects our observations, and whether it solves the mystery or just adds to it. If this video made you see the Milky Way differently, hit that like button and subscribe to Space and Scale. Next time, we're exploring the real reason we can't travel faster than light. And it's not what you think. See you there.